All right. Hello, everyone. Thank you all for coming. It's good to see you all here. So let's get started. In my previous talk, I talked about the fundamentals of machine learning. If you have missed it, it's no problem. I'm going to be recapping things, and this one is going to be, for the most part, independent from the previous one. So let's start with a recap. What is machine learning? If I had to explain it in 3 words, I would say learning by example. So in machine learning, instead of writing a set of rigid instructions to solve a problem, we design models that can learn to solve a problem given a set of training samples. And what type of problems machine learning can solve? Scene detection, object recognition, text translation, and like sentiment analysis, image quality analysis, which will be the topic of my next talk, and there are many others. So there are many ways to design machine learning models, and one of them is to use the artificial neural networks. And artificial neural networks can be considered as rough, very rough mathematical models of simplified versions of biological neural networks. So you may wonder why, like you're not neuroscientists, why are we interested in modeling human brain? Although that's also an interesting topic, as computer engineers and programmers, we're not interested in describing the brain, but we're interested in building useful machines. But we have an incentive to model biological neural networks because there are still many problems that humans perform better than computers do, and imitating the way the brain solves these problems can help achieve and sometimes even surpass human-level performance. So to model a neural network, we can start with modeling a single neuron. And here's a figure that depicts a biological neuron and how it's modeled in a computational model. So the biological neuron receives a signal from other neurons, as you can see in this figure. Let me move the microphone a little bit. So yeah, it receives the signal from other neurons, as you can see here. And how it's modeled here is we have the inputs, x1, x0, x1, x2, and so on. And the biological neuron accumulates the signal where the synaptic strength determines the influence of each input in the cell body, and how it's modeled in the artificial neuron is in the cell body we just get a weighted sum of the inputs. And the biological neuron fires if the accumulated signal is above a threshold. And this is simulated by using an activation function that I'll talk about later. And the learning in a biological neuron happens by adjusting these synaptic strength between pairs of neurons, which is simulated by learning the weights, adjusting the weights. So how do we learn these weights? Let's start with a very simple example and learn a linear function, y equals to xy, from data. It's a very simple model. It's a single neuron. It's not a neural network. And it has a single output, single input, single output, no bias, and linear activation. So first, we need to define a cost function here, which we want to minimize. And here we define it as the squared error between the observed output and the output of the neuron, which is the input times the weight. Since we don't have an activation function, it's just a linear weighted average, or just like in this case, we don't have multiple input, so it's just multiplication of these two. After what we do is we compute the derivative of this error with respect to our weight. And this is called the gradient, and it gives us the rate at which the error changes with respect to the weight, and it guides us towards minimizing the error by adjusting the weight here. And this is going to be our update rule at every iteration. Here, alpha is the learning rate, and this is the gradient, which is the derivative of the error with respect to w. And at every iteration, we update this. So in this very simple example, we have only these data samples, and we're gonna see them one by one. our batch size is going to be 1. And this is also called online learning. If you were looking at them all at once, this is called batch learning, but we're going to be looking at them one by one. So here in our update rule, alpha is the learning rate. It's a common practice to start with a relatively higher learning rate and reduce it gradually, which is actually analogous to human learning. As we are kids, we learn faster, and as we age, like we start learning slower and slower, which is usually considered a bad thing for humans, but for computers it might not be a bad thing, because it's easier to fool a child. Like if you give a mislabeled example, the child would believe it, but it's harder to fool a adult person with mislabeled information. Same applies to artificial neural networks. So after some time of training, the learning rate will be lower, and it's going to be more robust against mislabeled data. What we do here is we start with a random weight. We initialize the weights randomly. We have only one weight here. Let's say it's 0.5. Let's assume that it's a random number. And then we get our first sample. It's x equals to 1 and y equals to 2. And then we plug the input in our formula. It's x times w, and our w is 0.5, and the activation of the neuron will be 0.5, but it should have been 2. So we update our weight with this update rule we defined earlier, and then our new weight becomes 0.8, and then we get another sample which is y equals to 6 for x equals to 3. And then we plug that in, and then we compute the error again, the gradient of the error, and then update our weight again. And the learning rate is also reducing here. So after just a few iterations, you see that the weight becomes almost 2, which is the underlying function here, y equals 2x. So this is called one epoch, going over the entire set of data once. This is usually done several times until convergence. So this is called stochastic gradient descent learning, and if you do it in batch, it's called gradient descent learning. So what makes neural networks powerful is the high degree of connectivity between the neurons and adjustable connections. So that's why, like, we can create, using the single neuron model, we can create a network of perceptrons. They're used interchangeably, perceptrons and neurons, by outputting of a neuron's output into another neuron. Here, one of the most fundamental methods is the multi-layer perceptron architecture. It's a multi-layer architecture. Here's a figure that depicts a multi-layer perceptron. It has several layers. The first layer is the input layer, which has as many neurons as the inputs. Each one of these neurons is connected to one input dimension. And the output layer has as many neurons as the outputs. For example, if this was an indoor-outdoor classification task, one of them was going to be the indoor neuron, and the other one was going to be the output neuron. And we also have hidden layers in between those. Here, there's only one hidden layer. And these layers learn to produce output that is useful for the next layer. So it adds a layer of abstraction. And more hidden layer means the model can learn more complex patterns. However, without having a nonlinear transformation between these neurons, the network reduces to a single linear model, because each one of these neurons basically do is taking a weighted average of their inputs, and they're all like linear functions, and weighted sum of linear functions is also a linear function. So to solve that, we use activation functions between those neurons. An activation function maps the input space into a different space in the output, and doing so introduces nonlinearities in the network, so that the network doesn't reduce to a single layer linear model. This is a very common type of activation function called the sigmoid function. I'll go back to activation functions But before that, I want to talk about how we train these neural networks. Here we have a simple artificial neural network, and for simplicity, only some of the connections are depicted in this figure. So how do we train this network? It's actually similar to what we did before. We are using the gradient descent algorithm. So to update, for example, this weight right here, W8J, what we need to compute is the derivative of the error with respect to this weight. So an efficient way to do that is to use the chain rule. We can compute this by computing the derivative of the error with respect to y first, and then y with respect to z, where z is our activation function, and z with respect to w. So since we start from computing the top of the network and then we go backwards, this algorithm is called the backpropagation algorithm. And during the training of this network, we go back and forth. We go like forward propagation means activating these neurons and forwarding the activations, and backpropagation means computing the partial derivatives of these errors using the chain rule, having a dynamic programming algorithm. So let's go back to activation functions. The sigmoid activation is one of the most popular type of activation. It squashes the input to the range 0 and 1, as shown in this plot. But it has a very undesirable property called the vanishing gradient problem. Here, as you remember from the previous slide, our update rule has the gradient that uses the chain rule, and one of the components of this formula is the derivative of the activation function with respect to the weight. So if you look at the derivative of the sigmoid function, it looks like this. And as the magnitude of the input increases, the gradient goes quickly to 0, like on this end and this end. It's almost 0. So this causes a problem, especially in deep learning models. If you stack those hidden layers on top of each other, we're going to have more layers and more activation functions, which will lead to smaller gradients, which makes it really hard to learn early layer parameters in deep learning networks. So the one solution to that is to use rectified linear units. They're very simple activation functions. It looks like this. They're very inexpensive to compute. It's basically the maximum of 0 and x. It doesn't suffer from the vanishing gradient problem because its derivative is basically a unit step function. But it has another problem called the dying neurons problem. So if a neuron has a large negative bias, and neurons can learn large negative biases if they get a large gradient update, for example, a large negative gradient update, then basically the neuron might never fire again. It might be on the left-hand side of this activation function all the time. And since the gradient flowing through it will be always 0, like there's going to be no learning at that point. The neuron will be dead forever, and there's no way of recovering from that. So there are some solutions offered to this problem. They're called leaky and parametric rectified linear units. So instead of what they do is instead of having it 0 on the left-hand side of this activation function, they use a small negative slope so that there's going to be still like some gradient, and the neuron can recover from near death, basically. So how do we determine this small negative slope? We can choose like just something arbitrary, or an alternative is to learn this parameter also using the backpropagation algorithm, and this is called the parametric rectified linear unit. So we talked about ReLU activations. So yeah, let's talk about a little bit about the loss functions. Training a neural network is essentially an optimization problem, and our goal is to minimize the loss function. We've already seen an example of this in the first example, and our cost function was the squared error. This is a common type of error function that is used in regression tasks, meaning that if you're trying to predict a continuous valued variable, then we usually use the mean squared error as our loss function, and we try to minimize it. For classification problems, on the other hand, one common type of loss function is the cross-entropy loss, which is basically a measure of divergence between probability distributions. Here, how we get the probability distribution of the classes is usually we use a softmax function at the output layer, so that every neuron activation in the output layer becomes the probability of that class. The softmax function, what it basically does is it squashes the inputs into the range 0 and 1, and they sum up to 1. So it looks similar to a probability distribution, and we can use the cross-entropy loss to compute the loss. So here, what do we minimize? We might minimize the error, which penalizes the misfit data, but we don't do anything about the weights. Should it impose any penalties on large weights so that simpler models are favored against more complex ones? And the answer is usually yes, and this is called regularization. And regularization keeps model complexity in control to prevent overfitting. I talked about overfitting in my previous talk. If we recap, it's basically the memorization of the training data without proper generalization. So if a model is overfit, usually it performs very well on the seen data, but it performs poorly on new data. And this is usually caused by having too many parameters for the data we have. And as the models get more and more complex, they become more prone to overfitting. So one way to tackle this problem is to use L2 regularization, which penalizes the squared magnitude of the weights. So it works it's pretty simple. What it does is it basically adds the squared sum of the weights to our cost function with a regularization strength lambda. Here, larger lambda means we have stronger regularization, and weaker means we're regularizing less. It also makes sense from a philosophical perspective not to introduce any complexities unless it's necessary, as the Occam's razor states that when you have two competing theories that make exactly the same predictions, the simpler one is the better. Another way of dealing with this problem in artificial neural networks is to use a dropout layer, which basically drops a neuron with some probability p during training. It randomly drops neurons during training, so it's essentially reducing the number of parameters during training, but during the test, we'll have the entire neural network. So here we have a figure that shows how the standard neural network would have looked like and how it looks like after applying dropout during training. And using dropouts also forces neurons to be useful on their own without relying on other neurons learning more efficient neurons, basically. So we're gonna shift gears here. Yes, please. I usually do both together, yeah. So especially in convolutional neural networks that I'll talk about, it's a very common practice to use it with fully connected layers. I'll come to there and explain it. So we're going to shift gears here a little bit and talk about internal representations of data. And this is something human brain is very good at. We're good at learning concepts. For example, look at these images. How similar are they? Like, if you think of it from a machine's perspective, they're not the same color, they're not the same shape, and they don't have the same texture. They look completely different. But we, as humans, we know that they're similar because we know what a chair is. We're familiar with the concept of a chair. Same applies to words. For example, how similar are these words? Awesome, fantastic, phenomenal, incredible. They all to us, they all sound similar, but if you look from a machine's perspective, they neither sound similar phonetically or look similar without the semantics. So that's why we have feature extraction in machine learning. I talked about it in my previous talk. Let's recap what it is. It's basically extracting feature vectors from raw data such as documents, pictures, videos, and sound that will be useful for machine learning algorithms. And traditionally, this has been done by manual feature engineering and filter design, and it requires using domain knowledge. So this is like a traditional pipeline for most machine learning algorithms before deep learning and artificial neural networks got popularized. So we get the raw data, and then we extract like some sort of features. For images, for example, it could be histograms or like edge orientations or like anything. And then we get the output, which is a feature vector that looks like this X, like X1, X2, X3, and then we feed that into a model to learn a relation between this internal representation of the data and the output. With the neural networks, actually, we can find an efficient representation of data while being trained on given tasks, and we don't need any kind of manual engineering to extract those features. Everything is learned from data. So in a sense, it's learning to learn. And it can learn to extract these features and to use them simultaneously during training. So for words, learning the meaning of words, there's a simple artificial neural network architecture called word-to-vec. What it does is, given a corpus of text, it learns the meanings of the words and phrases in context. It's similar to how a child learns a first language, basically. It looks at the neighbors of a word in context to make a sense of it. So how it works is it assigns a random feature vector to each word in the corpus, and the corpus is a body of text, and then trains words against their neighbors. There are like two different architectures. One of them is called the continuous Bagel words architecture. What it does is it tries to predict the word looking at its neighbors. For example, let's say we have a corpus that includes this sentence: "My new Moto Z is awesome." And here, the inputs will be the vectors for my new, is, and awesome, and the output will be the Moto Z. And in the skip-gram architecture, it's the opposite. It takes Moto Z and it tries to predict my new, is, and awesome. But the goal here is not to actually predict these words. It's to learn the internal meaning of these words. So it's not actually trying to predict it. This is how the model is trained to capture the meaning of these words in some feature vectors. I ran this I ran some queries on a model trained on the Google News dataset on about 100 billion words. Here are some example queries and what I got. For example, the vector for the word phenomenal returned the words, vectors for the words incredible, amazing, fantastic, and unbelievable. So it was able to retrieve similar words, and it didn't use any dictionary or like it didn't have anything. It was able to learn it in context. So same for like Chicago, for example, it was Baltimore, Denver, NYC, and Atlanta. For cats, it was felines, cat, pets, and kittens. It gets more interesting. It can also learn logical analogies, and since we represent these words as vectors, we can capture some analogies by just using simple vector subtraction and sum. For example, the vector subtraction and sum for king minus man plus woman would be something very similar to a queen. Here I ran some queries on the same model to see what kind of analogies it could capture. For example, Berlin is to Germany as Paris is to France. He was able to capture country and capital relationships. So a cat is to a kitten, a dog is to a puppy. He was also able to learn the juvenile counterparts of these pets. it was able to capture even like more complex analogies, such as Toyota is to Lexus is like Honda to Acura. It was able to capture upscale versions of these car brands. And sometimes it finds like even more interesting patterns, such as a nerd is to a hipster is like engineering is to design. So using artificial neural networks, we can also learn how to represent images. And one way to do that is to use convolutional neural networks. A convolutional neural network model is a variant of multi-layer perceptrons that is inspired by the visual cortex, and their building blocks are called the convolutional layers. How they're different from the fully connected multi-layer perceptrons is showed in this figure. Assume that this is an image, and each one of these little boxes are pixel values. And in a fully connected layer, each one of these pixels would be connected to each one of these neurons. So everything would be connected to everything, and that would be a lot of parameters. In convolutional layers, on the other hand, these neurons are locally connected, and they're weight-sharing neurons. So these neurons, for example, connected to an image patch here, and then this is like a sliding window. It's the weights are the same for every part of the image. And the idea here is, like, if a feature is useful in one part of the image, such as like an edge, detecting an edge, if it's useful in one part of the image, it's probably useful in the other parts of the image too. So convolutional layers basically learn image filters, and each one of these filters are called kernels, and we can compute their activations by basically performing convolutional operator. If you're interested in human brain analogies, here our filter size corresponds to the receptive field of the neurons in human visual cortex. We can build convolutional neural networks with stacking convolutional layers on top of each other by feeding the output of one convolutional layer to another one. It's also common practice to use pooling layers between these layers, which basically downsample the input. How it does is it again has a sliding window, and it takes either the maximum value in this frame or the average of it. And doing so downsamples the input, and this provides translation invariance because if you have an object that we want to recognize, for example, in the image, and if it moves a little bit, the translation will be high in the first layer. But as we progress and as we keep having like more pooling layers in between these convolutional layers, the translation will be smaller and smaller. And also this provides us computational efficiency because the activations of these convolutional layers become smaller and smaller, which makes the computation of these convolutions cheaper. Here's an example convolutional neural network called AlexNet. It's pretty popular. It's been trained on a dataset of 12 million images, and it's trained to classify these images into 1,000 classes. So this is how the architecture looks like. It has a convolutional layer followed by a pooling layer, and then it has the same pattern, and then more convolutional layers. And at the top, there are fully connected layers, which are basically the same as multi-layer perceptrons, where every input is connected to every output. So what's interesting about this architecture, or like the convolutional neural networks in general, is layers learn to extract features, and we don't have to manually engineer filters. It basically designs the filters by itself. Here, for example, there's an illustration of the first layer parameters that were learned completely from data. So none of these filters were designed manually. They were all initialized as random values, and it was able to learn some useful features after being trained on all these images. So these parameters look interesting because they look similar to neurons in the primary visual cortex, and this is basically the primary visual cortex of this network. It's the first convolutional layer. And we observe like Bohr-like filters, like edge detectors here in different orientations and different scales. And we also have color contrast sensitive filters learned here. They detect like colors and textures probably. And here each layer can capture a higher level and more abstract set of features than the previous one. So as we go higher and higher, like they both learn to have a better representation of the input in the output. Here how the layer activations look like, some of the layer activations look like. This is a picture of a cat that I took in Cappadocia. This is the first layer activations. This is how it looks like when we apply the filters that I visualized in the previous slide. When we apply those image filters to this image, this is what we get. As you can see, there's like nothing very high level or abstract. It's responding high to like edges at different orientations or like different color contrast, but it doesn't have, for example, a cat neuron that fires only if there's a cat in the picture. But as we progress in the higher levels, for example, here I also visualize the fifth layer neuron activations. They try to capture more complex things in the image. Here, for example, you see like some dots and they're placed where the cat is. They might either be cat neurons or they could be like pet neurons or like animal neurons. They could be responding to higher level objects in the image. And we feed these into the fully connected layers. And at the end of the network, what we get is domestic cat with 0.74 probability. Sure.
So I didn't really understand what the whole point of that. Like you start with that image of the cat, and what are you trying to do? Like in the
So what I'm trying to do here is to illustrate how a convolutional neural network learns a hierarchy of features. So the first layers learn like simple features such as edges or like color contrast, kind of simple things, and then like the next layers start to learn object parts and like common things shared in similar scenes. And at the top of the network, it learns what a cat is.
So you're feeding that image so that it learns that that's a cat?
No, this is a test sample. So the question is if it's learning this cat from the sample. No, this is not the training sample. This model has already been trained with like many images, and some of them include pictures of cats. And this is just a test sample. After the model is trained, I'm giving the model a sample to classify. Any other questions? Yes, yes. And also there are like similar labels such as a Siamese cat. That's why it's not 100% probably. So the thing about convolutional neural nets is training them requires a lot of training samples. And we usually have smaller data sets. But if you have similar problems, we have an option. Instead of training everything from scratch, we can fine-tune an existing model. So this is also called transfer learning. We can borrow parameters that were already trained on another task to train it on our problem of interest. So how it works is we start with a pre-trained model, and then we reduce the learning rate of the earlier layers so that we are not trashing the parameters of these general layers. And the first layers usually learn like very general purpose features, so it's really not necessary usually to change them too much. So one approach is to fix them completely and then train only the later layers. But it's a common practice to have a lower learning rate for the early layers and then fine-tuning the later layers. For example, we can fine-tune an object recognition model to create a scene detector. But we can even do like we could even use it for like more different tasks. This is very similar, like for object recognition and scene detection, they're very similar tasks, and we could even do that by just fine-tuning a single layer. But it comes with a cost. It limits our architecture. We end up with a less flexible model architecture, because if you want to borrow parameters from an existing model, our layers should match them. So we can't have like completely different types of layers and borrow these parameters. For the layers we are borrowing, they need to have the same architecture. If you have, yes, please. What do you mean by the cost?
If I want to test something,
Oh, it depends on the cost. The problem, the question is how costly it is to the compute, like not to train but to test the system for a given sample. So it depends on the type of the architecture. It depends on how many parameters you have and how deep the model is and what kind of hardware you're using. If you're using GPU acceleration, it's just like milliseconds. But if you're running it on CPU, it might be like seconds. And it totally depends on the type of the architecture, number of the parameters, and the type of the hardware you're using. So if you don't have any labeled data at all, you can still learn. It's still possible to train artificial neural networks without having any labeled data. And this is called unsupervised learning. I talked about it in my previous slide. It's basically learning without labeled data. And in artificial neural networks, one architecture is to use these hourglass-shaped neural networks. They're called autoencoders. What they do is they try to reconstruct the input in the output. So you may ask, like, what prevents it from learning an identity function? So how can this even be useful? So here, the bottleneck prevents that. It forces the network to learn a compact representation of the input. Since the number of hidden units is smaller than inputs, the model learns how to represent the input using a smaller feature space. So how we can use it? We can use it for pre-training if you don't have enough labeled data, but if you have some, so we can pre-train it with unlabeled data first, and then train for our labels, as in deep belief networks. And we can also use it for dimensionality reduction or feature extraction, as the network learns to represent the input in a smaller feature space. Here's a recent paper titled "Building High-Level Features Using Large-Scale Unsupervised Learning." It's really interesting. They use a 9-layer locally connected autoencoder neural network architecture, and they trained it on 10 million images captured from YouTube videos. So it's basically like a computer sitting in front of a computer and watching YouTube videos for a week. So what it learned was interesting. It learned neurons respond strongly to frequent patterns. And here are some illustrations of the neurons it learned. It learned human faces, and it learned cat faces, because there are a lot of cat videos on YouTube, and it learned human bodies. Let's talk a little bit about an interesting topic, computational creativity. Can computers paint original paintings? Most people will say no. So here's an example paper. It's a recent paper titled "Image Style Transfer Using Convolutional Neural Networks." What it does is it transfers the style of painting to a picture. Here, there's a figure from the paper. This is the input picture, and the ones here are the reference paintings, and this is how the result looks like. It basically paints this picture in the given style. And how it does is it uses a pre-trained convolutional neural network, and then it uses two different type of loss functions. One of them is designed to capture the content, and the other one is designed to capture the style. And they start with a random noise image and then iteratively synthesize a new image that minimizes both of these types of loss simultaneously. So basically, it's not an image filter. It's not filtering the original image. It's painting it from scratch. You may say that this is not original enough, the previous one, because it doesn't dream, like it doesn't have imagination. It just takes an image as an input and then takes a painting. It takes a picture and a painting as inputs and then recreates one of them in the other one's style. But we can go further. There was a blog post from last year called the Inceptionism, Going Deeper into Neural Networks. That was a blog post from Google Research. And what it does is basically it takes an input image and then it overinterprets it. It says like whatever you see there, make it look like more like it. So it hallucinates basically. For example, if this cloud looks kind of like a dog, in the next iteration it's going to look like more like a dog, and then more, and then objects will start to emerge after some iterations. And the input doesn't have to be an actual natural image. It can even be random noise. And this is how your artificial neurons dream on LSD, and LSD stands for large-scale data. These images were all created from pure noise, pure random noise, and how they generated it was to run this deep dream algorithm, and after every iteration, they zoomed it a little bit and fed the output of the iteration as the input for the next iteration, and this is what they got. No, it's automatic. Actually, its source code is available on GitHub, so you can create your own dreams. So how do we implement this? Luckily, we don't have to implement it from scratch. There are libraries, useful libraries that do the hard work for us. And some of the most popular ones are Caffe, TensorFlow, Theano, and Torch. I'm going to talk a little bit about Caffe. It provides support for many types of the layers that are used in convolutional neural networks, including convolutional layer, pooling layer, fully connected layer, and loss activation, and other layers. And if you need something else, it also lets you to implement your own layers in Python. You can also do that in C++, but it's easier to do on Python. And how the models are defined is they use a protocol buffer definition file to design neural networks. Here's a snippet from a model definition file. It's pretty straightforward. Here we have a layer named conv5, which inputs data from a blob named conv4 and outputs into conv5. And here blobs are 4-dimensional arrays. It inputs from this and outputs to there. And we define its parameters here, like number of outputs is the number of neurons, and padding is like how much padding we have. And kernel size is the size of the receptive field, basically. And then we define our activation function. It's a rectified linear unit. Here, it's defined in place. It doesn't use another. Yes, please. Oh, okay. So it doesn't use extra memory to implement it. It's defined in place, and we have a pooling layer defined here, which takes the data from conv5 and feeds into pool5, and then here we have the parameters. For example, it's a max pooling layer, takes the maximum for each window, and we define the kernel size and step size. And on the top of it, we have a fully connected layer. We can define multi-layer perceptrons also using these fully connected layers. To start training, we also need to configure the solver. It also has a configuration file that looks like this. It has an we can set our optimization algorithm and choose the learning rate and define the learning policy using this configuration file. And what I like about Caffe is, one of the things I like about Caffe is they have a repository called the Model Zoo, It's a user-contributed repository of pre-trained models. You can use these models as is, or like you can use it to fine-tune your projects. There's a variety of pre-trained models in the model zoo. So this concludes my talk here. In my next talk, I'm going to be talking about perceptual image quality analysis. I'll be talking about full reference and no reference image quality assessment, and I'll talk about natural scene statistics, how we define no reference image quality assessment models. And I'll also talk about a model I developed here called the General Image Quality Index, which is a deep learning architecture. It's a no reference image quality model that predicts human opinion on image quality. Thank you all for listening. Do you have any further questions or comments? Yes, please. Yeah, so the question is, how do we test these models? That's a general machine learning problem. It's not only about deep learning. Usually we have a separate test set and training set, as you've said. But you said if you have a different test set, the results might be different. So that's a problem for designing test sets. Usually like random splits work, randomly splitting the data into like 80% training, 20% set test, for example. It's not any different from like any other machine learning problem in that sense. Yes, please. A little bit. I use it only for Word2Vec, but I use Café most of the times. Oh, yeah, and I think it's faster also. Café is a little faster.
So Leo, is Café though more oriented for image processing?
Yeah. It's the question is if Café is more oriented for image processing and computer vision. Yeah. TensorFlow is, I think, more general purpose. You can define things like Word2Vec or LSTM models, and you can do like natural language processing and also like computer vision. Thank you all for listening.
Thank you, Leo.
And that's it for today.